This video is on calculating voltage for a voltaic or a galvanic cell and standard reduction potentials. Okay, so just as a reference, here's the voltaic cell we were just talking about, and we're going to use this as our example in terms of how did they, could we have calculated this number on paper, instead of using a voltmeter like this, reaction did. Okay, so the discussion here is, well, what's the driving force behind this reaction? So we know voltaic or galvanic cells are spontaneous. Means they have a negative delta G, right? And it's due to the electrons, okay, due to the motion of the electrons. We also know that galvanic or voltaic cells are going to produce a voltage. So notice that in my picture, this voltaic cell produced a voltage of 1.1 volts. Okay, it's a positive number. That means that this reaction is spontaneous, and we're going to make that connection at the end of this lesson. Okay, so why do these things work? Driving force is the movement of electrons, the oxidation of one thing, the reduction of another. Okay, so moving on, a couple of terms to talk about. The first one is electromotive force, or EMF, and this is the potential energy difference or the voltage difference between the two electrodes. And then the cell potential or the cell voltage, okay, is what's the voltage produced by this reaction. And we label that as E of the cell, okay? E, I know, throws us off a little bit, but it's for the electromotive force. It's a voltage, or it's going to be in units of volts. Spontaneous reactions are going to have a positive voltage or a positive E cell. Okay, so the discussion is going to be how do we calculate that number in just a minute. And then we have what we call standard EMF or standard cell potential, or I guess standard voltage. And this, as you might guess, is the cell potential or the voltage under standard conditions. We have lots of discussion about standard conditions. It's a temp of 25 degrees Celsius. Our table that we're going to look at even says that. And 1 molar concentrations of ions, I guess, is the right thing for us to say. We know that what's going to happen is we could have a situation where it's not standard conditions, but that's not this video. Okay, and we label that E cell with the not symbol. It looks like the degree. We know that that means standard conditions. Okay, so could we have predicted the voltage for the cell to be 1.1 volts? That's the question. So what we have to look at is a table, okay? And so I put this picture in here. And this is a table of standard reduction potentials. I want to draw your attention to that very quickly, that these are, every single reaction in this table is a reduction reaction. That's just how they're presented. It's just the notation that was adopted for this. Okay, notice none of these reactions are oxidation. They're all reduction. So these standard potentials are presented as reduction half reactions. Okay, that's in this table, that's in any table that you look up, that's in anytime you go to Google and Google something, it's going to give you the standard reduction potential, not the oxidation potential. And as we can see from the table, some are larger positive numbers and some are larger negative numbers, okay? But these are all reduction. And so if we wanted to come up with the oxidation potential, you know that a reduction and oxidation are a reverse of each other. And so just like kind of in our thermochem discussion, if you were to flip a reduction reaction, like in the chart, to turn it into an oxidation reaction, you would change the sign of the reduction potential. Okay, so it's pretty simple, and most students don't have a hard time with that. Okay, so let's revisit our cell real quick and write these half reactions and figure out if we could have calculated the voltage. So we know in this case at the anode that oxidation is occurring. Zinc's losing 2 electrons, turning into zinc plus 2. We know that at the cathode, reduction is occurring. Copper plus 2 is turning into copper solid. So let's do that as half reactions. So we know that the oxidation half reaction is the zinc losing 2 electrons, becoming zinc plus 2. And we know that the reduction reaction is the copper gaining 2 electrons, turning into copper solid. Okay, so we can calculate the cell potential if we know the oxidation and the reduction potentials. And so we have this chart. So of course, only one of these reactions is going to be in this chart, and it's going to be the reduction reaction, because remember, they're all reduction. So we kind of weed through this chart. We look for the copper plus 2 plus the 2 electrons. There's copper plus 1 electron. That's not it. There it is. Copper plus 2 electrons. And its reduction potential is 0.34 volts. Okay, so E reduction is 0.34 volts. Okay, and so now what I can do is, even though, yes, I know I wrote reduction, but even though this reaction is oxidation, I'm going to go to the chart and find this reaction as reduction. So it would be the reverse, right? Zinc plus 2 electrons. So let's find it. Zinc plus 2 plus, there it is. Zinc plus 2 electrons makes zinc negative 0.76. Okay. However, that's for the reduction. And we know that this reaction is not reduction, it's oxidation. So we're going to flip its sign and we're going to say the cell potential for the oxidation would be 0.76 volts. And then when I know the oxidation potential and the reduction potential, as you might guess, I can find E of the cell at standard conditions by adding them together. And we proved that this cell actually does or should create a voltage of 1.1 volts. Notice it's positive, which means that it's a spontaneous reaction. Okay, so that's how you use the table of reduction potentials to find the cell potential. Now there's a couple practice problems that we'll do, but before I do that, I want to say one more thing, which is that reduction potentials are an intensive property. Okay, and you might not remember what that is, but density is an intensive property. So if you can remember, way back when we learned density, we said it doesn't matter what kind of piece of gold I have. If I have a gold ring, a bar of gold, a coin, a necklace, it's going to have the same density because it's a ratio of mass to volume. So the same thing is true for these standard reduction potentials. Okay, so whereas in thermochem, if you double a reaction, you'd have to double delta H. Okay, that's because delta H is an extensive property. It depends on how much you have. But standard reduction potentials are like density. They're intensive. So it does not matter how much of something I have or how many electrons are being transferred. The standard reduction potential is still the same. So if we had to triple or double one of these reactions, the reduction potential is just the same. It's just what it is in the chart. And sometimes that's hard for students to understand, but we're going to see that in one of these practice problems. So this is a takeaway, definitely. Okay, so let's do a practice. And actually practice 1 is, we actually already know the answer, but we can still do it anyway. So it says, I slimmed this down for lack of time here, but it says for this zinc copper voltaic cell, we have this reaction. We know that the E of the cell is 1.1 volts. Okay, and then they tell me that the reduction potential when zinc plus 2 turns to zinc is negative 0.76 volts. Calculate E of reduction for copper plus 2 to copper, assuming we didn't have the chart. Okay, so how do we do this? Well, this is a different one because just a minute ago we solved for E of the cell, but what we're looking for now is one of the potentials. So we have to break this down into the two reactions that are occurring. We know zinc is going to zinc plus two electrons. That's oxidation. And we know that copper plus 2 is going to copper. That's reduction. Okay, so they're telling us to calculate the reduction potential for this. Okay, we're pretending like we don't know it. Well, and if we don't have the chart, then we don't know it. And they tell us that that the reduction potential for zinc plus 2 going to zinc is 0.76. So then for this reaction, right, which is the oxidation, would be positive. And I know that E of the cell is 1.1. So this is where we say, okay, well, we know E of the cell is E reduction plus E oxidation, 1.1 volts equals question mark plus 0.76 volts, right? Or I guess I should have said X. That would have been better. Okay, and solve for X, right? Subtract 0.76 from both sides, and we end up with 0.34 volts, which should be the reduction potential of copper plus 2 going to copper. We could confirm that in the chart, and it is. Okay, second practice problem says the voltaic cell is based on the half reactions of this and of this. The cell EMF is 1.46 volts. Using a data table, calculate the reduction potential for when I plus 3 turns into I plus. Okay, so I'm looking for E of the reduction for this, right? But we should quickly say, wait a minute, this is the reduction reaction. This is the oxidation reaction. So I know E of the cell, which means I need to go to my table and find the reduction potential for when Br2 gains 2 electrons. Br2 gains, there it is. When Br2 gains 2 electrons, 1.09 is the reduction potential. Right, I don't need to flip a sign because this is in fact reduction. What I'm looking for is E reduction, careful of this, so the reverse, but I'm going to treat it like oxidation, right? Because I know that E of the cell is equal to E of reduction, half reaction, plus E of the oxidation reaction. We're saying it's the oxidation reaction that I don't know, right? We're calling that X, and I know that E of the reduction reaction that's occurring is 1.09. Solve for X, take 1.09 to the other side. We end up with 0.37 volts equal to X, which is the, careful again, the reduction potential of that reaction. But, oh my gosh, I'm sorry, I just misspoke. That's the oxidation. Goodness gracious, right? Oh, I just erased it instead of meant to circle it. That's the oxidation potential. Whew, see, I did it. You can easily do it. And they're asking me for the reduction, which means the reduction potential for that is going to be the opposite sign. Because remember, what we're given is oxidation, but they're asking me for the reduction potential. So it's going to be negative. And then the third one, using the data table, calculate the E cell for the following reaction. They're giving it to us in one big chemical reaction. So we need to split it into the oxidation and reduction half reactions. So let's look at this. Oxidation is, oh, I forgot my 2 here, sorry. Oxidation is the 2 aluminum turning into 2 Al plus 3. And think about how many electrons are being lost. If aluminum turned into aluminum plus 3, it would be losing 3 electrons, but it's 2 of them, so it's losing 6 electrons. And then reduction must be the 3I2 turning into the 6I minus, which is a gain of 6 electrons. So there's my 2 half reactions, and I need, I need the reduction potentials for both of them, right? And then I'll have to flip one sign to find E cell. So 2 aluminum going to 2 Al plus 3. Now that's probably not going to be here because that's a doubled situation. This is the one I was referring to. So aluminum going to aluminum plus 3. Aluminum. Is it not here? Aluminum. There it is. So, oh yeah, remember this is oxidation. So aluminum going to aluminum plus 3 is oxidation, but aluminum plus 3 going to aluminum is reduction. So negative 1.66 is the reduction potential for this reaction. Now you might say, shouldn't we double that? No, we should not double that because, again, remember, intensive, we just pull the reduction potential straight from the table. And then this one should be in the table as written, except I don't think it's going to be 3 and 6, right? It's going to be 1 and 2. So I2 being reduced to I minus, I2 being reduced to I minus, here it is, 0.54, that is a reduction reaction. Okay, and then I say, okay, E of the cell is E of the oxidation plus E of the reduction. E of the oxidation I don't know, but I do if I just flip its sign. So I have two positive numbers then to add together. And what is that? 1.66 plus so 2.20 volts. Positive is the motive force or the EMF or the cell potential or the voltage of this voltaic cell, and you would absolutely say, oh yes, this is definitely a spontaneous reaction, is producing a positive voltage. Okay, so that's how you can use standard reduction potentials to find E of the cell. And the only thing you have to keep in mind is that any number you're given in a table is going to be a reduction. So